Hello everyone and welcome to McLean 360. So in this video I want to look at deflections and axial loadings with you. Alright, so let's read the problem together and solve it. Alright, so we have two cylindrical rods, one of steel and other of brass, are joined at C and restrained by rigid supports at A and E. Now for the loading shown and knowing that ES, so ES for steel is 200 gigapascal, and then for brass EB is 105 gigapascal. So our task is to determine the reactions at A and E, so RA and then RE. Finally, we should find the deflection of point C. So the deflection at this point. All right. Okay, so let's sort of try and draw the free body diagram of what we have here. Okay. But then, okay, let's do it this way. Let's calculate the areas. Okay, let's calculate the areas. So we have two structures. We have AC, and the AC is steel, right? So let's calculate the area there. So the area for AC for the steel part is what? The diameter is 40 mm. So it's going to be pi times 40 squared over 4, which is pi d squared over 4. So it's going to be pi multiplied by 40 squared over 4. And what is that? 1256. So 1256.63. Or let's say 1256.637 millimeters squared. Okay. So now we know the area from A to C. Let's calculate the area from C to E. So area from C to E. So that area is going to be pi. The diameter there is 30, right? Okay. Over 4. So I will just clean the 40 and make it 30. And that will give me 706.858 millimeters squared. So now I have the areas. All right. So now what can we say? We know that E is what? Okay, let me just go straight forward and draw the free body diagram. We want to sketch this, the free body diagram. So it's going to be something like this. We have steel here, and then we have brass here. Okay, so steel and brass. Now there is this support here, so it's going to be reaction, and then also there is the support here. So let's call the reaction at this support RE, and then let's call the reaction at this support RA. Now if you look at it carefully, you see that there are some sort of forces acting at B. So we have A, we have B, we have C, we have D, we have E. So this force is what? 60 kilonewton. Then there is another force here, which is what? 40 kilonewton. So this is the free body diagram of the structure here. Now we have to find, first of all, so the question said we should find the reaction at A and B, but we need to start from somewhere. So let's begin by solving for the reactions at let's find the deflection in AB. So the deflection in AB, the deflection in the steel, that's what I want to say. So AC, the deflection in the steel will be the load times the length, area divided by the Young modulus for steel. Okay, let me just go straight forward. So now it's going to be the load in the steel. But what is the load in the steel? So look at it carefully. Now, to be able to know the load in the steel, we have to take our time and do it section by section. So maybe let me clean this one. I will start from A to B. Please, we want to take our time and solve the question. So we want to look at from A to B what is happening. If you want to know from A to B what is happening, you just section this portion, and when you section that portion, you are going to see something like this. And then there will be RA here. Therefore, what you have here must be F, or let's say the PAB. In other words, all right, so looking at this portion only, then we can say that PAB is actually RA. This is interesting. So if I cut only AB through, then I can say that I have RA. Therefore, if I am calculating the deflection in AB, it's going to be RA multiplied by the length. But what is the length? The length is 180. So 180 mm divided by the area. What is the area? So as for the area from A to C is the same area. So that one is 12.56. Okay. So 12.56. Then I will multiply it. Okay. So 12 point, oh sorry, it is 1256.637. okay, so 0.1, no, 180 millimeters. Please, let's stick to millimeters. 180 mm multiplied by RA divided by 1256.637. Then I'll multiply it by the, so we are using this formula PL over AE. I'll multiply it by the Young's modulus, which is for the steel, and that is what, 200 gigapascal. So it's going to be 200 times 10 to the power 3 megapascal. All right, so if I do this, what is going to happen? So from A to B, the deflection in terms of RA is going to be, let's pick our calculators and do this. So it will be 180 divided by 1256.637 multiplied by 200 times 10 to the power 3. So we have 7.162. 7.162 times 10 to the power minus 7 in terms of millimeters. All right, so that is what we have. Now let's look at from B to C. It's getting interesting. So what we have here is just from A to B. Okay, from A to B. Now let's do from A to C. B to C, sorry. Let's do from B to C. So from B to C, I don't want to draw the whole thing again, but instead of sectioning between A and B, I'll rather section between B and C. Okay, let's not forget that this is 60 kilonewtons. So I will section between B and C. If I do that, this is what I will get. I will get the whole of this structure here all the way here, but there will be a section. Now this is 60, and then I have RA here. So this should be what we have here is supposed to be our load, which is PBC. So from equilibrium, we can say that our summation of forces, every force in this direction is positive, should be 0. So we can say that minus RA plus 60 plus PBC, all right, should be 0. So then we can say that PBC so PBC will be RA minus 60. All right. In other words, to get PBC, it is RA minus 60. Having known this, so we are doing from B to C. Now, having known this, we can go ahead and say that the deflection in BC will be the load. Now the load is the RA minus 60, right? Then we multiply by the length of BC. So what is the length of BC? 120 mm. All right, so 120 mm. Then I divide this by the area. As for the area of AC is the same. So you don't need to calculate the area again. It's going to be 1256.637. So 1256.637 for the area, and then for the E is the same thing because it's also steel. All right, so that one is still the same thing because it is steel. 200 times 10 to the power 3. So that one, okay. So then delta BC will be what? RA minus 60 will be there. We can't do anything about it. So let's just solve for whatever we have for this one. So 120 divided by 1256.367 multiplied by 200 times 10 to the power 3. And what is that? So we have 4.776 times 10 raised to the power minus 7. All right, so this is what we've got. So from B to C, this is what we are getting. All right, in terms of millimeters, don't forget that the answer is in millimeters. All right, so we have done AB, we have done BC. We need to do C to D. It's getting interesting. Now, if we do C to D, what are we going to get? So let's do it together. From C to D, it means that our section, okay. So No, let me use what I have here. So from C to D, it means I will come to C and D and I'll take a section here. Okay. Then if I draw it, I'm going to draw everything with the exception of okay, let me just draw it. So from C to C, from C to D, I'm going to get something like this. So RA will come as usual, and then so if this is point A, C will come. So okay, it's going to be like this. B will come, and we know that there is a load of 60 kilonewtons at B. So that one will come, and then C will also come. So let's say that this is C. So C will also come, but I have cut between C and D. So it means I need to extend. Okay. So I'll sort of extend out here, and then extension is going to give me PCD. So if I cut between B and C, C and D, then I have PCD. Again, let's do some sort of force balance. In fact, it will just be the same as BC, because if I sum forces, every force here to be positive should be 0, minus RA plus 60 plus PCD to be 0. We can say that PCD will be RA minus 60. So meaning that between BC and CD, there will be the same sort of force which will be experienced. All right. So we know PCD, right? Okay. Again, deflection in CD will be the load, which is RA minus 60 multiplied by the length. What is the length? So the length is 100 between C and D, right? So 100 millimeters divided by area. So the area will be the brass portion, which is CE. So it's going to be 706.858. So 706.858. And then so so we are using this formula PL over AE. Now we have the load, we have the length, we have the area. So the E that we are going to use this time is going to be the brass, which is 105. So 105 multiplied by 10 to the power 3 delta CD. So we can't do anything about this one. Okay, so let's just compute the in fact it's almost the same. No, let me change it. It's going to be 100 millimeters, and then I'm dividing this by 706.858 multiplied by 105 times 10 to the power 3. And what is that? 1.347 times 10 to the power 6. 1.347 times 10 to the power 6. So this is the expression for the deflection. All right. So this one is also what? From C to D. All right. So finally, let's do D to E. So let's do D to E. Then, okay, let me go back to the actual structure. So this time around, I will take the section or the cut between D and E. I think by now you should know how to do this. All right. So this is actually application of internal forces. Okay. This is application of internal forces. So let's draw what will happen. So you will get A all the way to C. So let's say this is A. Let's say this is the reaction at A. There is a load of 60 kilonewton at B, and then there is some sort of okay, there is nothing at C, but there is a protrusion where the brass comes in, and then all the way to D. Watch this. At D there is 40 kilonewton, but it will go beyond it. So it's like at D there is 40 kilonewton, but we will go beyond it, and that is where we are. We are going to cut between D and E. Let's call this PDE. All right. Now from here we can see that summation of forces along X positive should be 0. So this is equilibrium, okay? Minus RA plus 60 plus 40 plus PDE should be 0. What is PDE then? PDE is nothing but RA minus 100. 60 plus 40 is 100. We don't need a calculator to do this, right? All right. Again, delta PDE will be what? RA minus 100 and then multiply by the length. So what is the portion of the length over there? 100. So the length is 100 mm. The area is the same as that of the brass portion for CD. So it's going to be 706.858. And then it is also brass, 105 times 10 to the power 3. So the funny thing is that ABBC is the same, and then CD DE is the same in terms of the area and then the Young's modulus. So delta DE is what? So we know that we cannot do anything about this. So let's compute that expression there. So it will be 100 mm divided by 706.858 multiplied by 105 times 10 raised to the power 3. So 1.347 1.347 times 10 raised to the power minus 6, and everything is in what? Millimeters. So this is the deflection of DE. Okay, so this one will also give us from where? So from D to E. So we have done quite a lot, but why are we doing all these things? We are doing all this because once we know the deflection, we can just use it to solve. Now, in fact, we are done. So what is the deflection from A to E? So the deflection from A to E, so the deflection from A to E will be between AB plus BC plus CD plus DE. Okay. Now, what do we know? So we know that okay, let's add it. Let's add all of them. So you know what? We are going to take our time and add everything we have. So I want to write it down. So we are going to add so for this one we got oh, we were supposed to multiply RA here. Okay. Okay. So we are going to add all of them. So let me quickly copy them and add it. All right, so I have done something. I want you to also do the same thing. So I want you to take your time and add all the RA component. So add this and then RA and then RA multiplied by this, RA multiplied by this. If you do that, which I have done here on the calculator, if you do everything, you are going to get 3.8878 times 10 minus 6 RA plus, okay, so I want you to also do the part without RA. So multiply 60 by this, multiply this by 60 again, and then 100 by this, and put all of them together. All right, so I want you to take your time and add everything which is not containing the RA. I've done it on the calculator. You will get minus 2.441, so minus 2.442 times 10 raised to the power minus 4. So this is the expression for delta A. But interestingly, if you look at this, this is actually some sort of statistically indeterminate. So you realize that the deflection at the end will be 0. Therefore, we can say that delta AE is equal to 0. So from here, this will be 0. Therefore, RA will be 2.442 10 minus 4 divided by 3.8878 times 10 minus 6. If you do this, what will be the value of RA? So as for this one, we can calculate it together. So 2.442 times 10 to the power minus 4 divided by 3.8878 multiplied by 10 by minus 6. And what is that? So RA is 62.8 kilonewtons. So RA is 62.8 kilonewtons. All right. Having gotten RA, what can we say? So, all right. Okay, so we have solved the first part, which says we should find reactions A and E. So let's find RE. Let's solve for RE. So to be able to solve for RE, we should not forget that so let me come here. Looking at the last portion, PDE, this one, you will realize that if you want to solve for okay, let me do it this way. So all what I'm trying to say is that if you look at this last portion, okay, if you look at this last portion and then you bring it here, it will be something like this. RE will be here, and then there is going to be PDE. But what is PDE? So PDE is RA minus 100. So RA minus 100, therefore it means that so if I cut, so I'm looking at this portion, RA minus 100. But what is okay, so it means RE is actually RA minus 100. That's what we are saying from the equilibrium reaction. That is, if you look at the section part, if you look at this right hand side, so RE will be RA minus 100, but RA we know, therefore it's going to be 62.8 minus 100, which is what? So minus 100, which is minus 37.188. So minus 37.2 kilonewtons. So the fact that we are getting negative means that RE is actually 37.2 kilonewton, but the direction will change. It means that RE is actually supposed to come somewhere here. So RE. All right. So that is RE for you. Now, the last part of the question, he said that we should calculate the the deflection at point C. Okay, so to get the deflection at point C, what do you think will be the deflection at point C? So the deflection at point C will be the deflection all the way here, meaning that AB plus BC. So it's going to be the deflection of AB plus deflection of BC. So we have to just bring it down here and then substitute the values. So what is it going to be? So deflection at C will be deflection at AB. What did you get? It was 7.162 times 10 minus 7 RA. 7.162 times 10 minus 7 RA plus the deflection in BC. So 4.776 times 10 minus 7. 4.776 times 10 minus 7 RA minus 60. So if you put everything inside, what are you going to get? Okay, let's put in the values. So 7.162 times 10 minus 7 and then multiply by RA, which is 62.8 kilonewtons times 10 to the power 3, plus 4.776 times 10 minus 7. RA is 62.8 times 10 to the power 3 and then minus 60. Okay, but the 60 there is also in kilonewtons. So 60 times 10 to the power 3. Now, if you do everything correct, what are you going to get? I want you to take your time and solve it. Then you will realize that the deflection at C will be 46. So 46.3 times 10 to the power minus 6 meters. Okay. So I want you to check this out on your own. So the problem has been solved. Thank you very much for watching.